Welcome to Astro Assembly 2022. We're very grateful that you all weathered the weather to make it here, and hello to our folks that are also watching. Fortunately, in this club, we have in skyscrapers, we have folks with a lot of talents, and we're blessed that they share them with us. So please help me extend a warm skyscraper welcome to Mike Corvese.
Can everybody hear me in the back okay? Yeah, I'm usually don't need a microphone. My wife's always telling me to, turn it down. Right? She says I have a PA system built into my chest, right? She's like, Mike, you're feeding back, turn it down, right? Tend to get a little bit loud. But thank you, Scott, for that introduction. But I will make one correction. My interest in the moon has not been over many years. It's really been just over the past year that I've had an interest in the moon. The moon, like too many of us, was kind of a bane for me. I'd cross out on the calendar when the moon was going to be out at night and say, okay, no observing on these nights, right? Because I want to go see the the faint and fuzzies, and the moon's in my way. But about a year ago or so, I started to get a little bit of interest and started looking at it a little more and started studying it, and found that there were a lot of interesting things to look at on the moon. And so in skyscrapers we started a lunar observing group, so we have that continuing. So if anybody is interested in joining that, we have a bi-weekly call where we talk about the moon and things that are going on there. I did a talk back in April that talked about the origins of the moon. So we kind of talked about how the moon was formed, this giant Mars-sized object, smacked into the moon, created this huge, debris, debris circle around the, ring around, and then it all coalesced into the moon. So my talk today is going to go from that point forward. Okay, once the moon was formed from this giant impactor, what happened after that? Okay, so the title of the talk is the evolution of the moon. Okay, and so the first thing we look at is scientists have put together a timeline, right? A lunar timeline with a named period. So they've got these 5 periods of lunar history. Okay, we've got the pre-Nectarian, Nectarian, Imbrium, Eratosthenean, and Copernican. Okay, what's that? That's all right. That's all alphabet soup. Nectarian is named
Mike,
for
excuse
Mare
me.
Nectaris.
We're not seeing the screen in Zoom land here. We're not seeing the screen.
Sharing the screen.
Your PowerPoint presentation. Yeah, that's what I'm seeing. I'm seeing you, and then just a little corner of the presentation.
Gotta love technology, huh?
Love-hate relationship.
I would stop screen share and restart it again. Would be my advice.
Yeah, perfect. Thank you.
Okay.
Sorry to interrupt.
All right. Continue.
Good job.
Yeah, excellent. Great suggestion. So as I was saying, so Nectaris, or Nectarian, the Nectarian period is named after the Mare Nectaris. And for those that aren't familiar, Mare is the Latin word for sea, okay? And Nectaris is the Latin word for nectar. So it's the sea of nectar. So all the seas that we see on the near side of the moon that are named, those are called mare. So you got the different mare, but they're seas is what they're called. So that's named after the sea of nectars. Imbrium is actually named for the Mare Imbrium, as you could probably guess. Imbrium stands for showers. So it's the sea of showers, and that's what it was named for. Now, when you get to the Eratosthenean and the Copernican, those are named for people, right? Eratosthenes was a Greek philosopher, also astronomer, mathematician. He was actually the first one that got a pretty good, not dead on, but a pretty accurate measurement of the circumference of the Earth. He was also able to measure the tilt of the Earth's axis. Okay, and you got to remember, this is back in 200 BC. right? He wasn't right on, but he was pretty darn close, right? For what he had, for tools to do those measurements. And then, of course, there's Copernicus, right? Who was later on in the, in the Renaissance, who was the developer of the heliocentric theory, right? Where the sun was the center of the solar system. Okay, so that's how they're named. So the first three, the pre-Nectarian, Nectarian, Imbrium, are named for events, all right, things that happened, right, on the surface of the moon. The Eratosthenean and the Copernican are really named for the kind of the ages of certain craters, and we'll get into that a little bit as we go in. So that's kind of the difference between those. And just to kind of put this in an Earth scale, just after the beginning of the Imbrium era is when prokaryotic life was first beginning to develop on Earth. So if you remember your basic biology, right? Prokaryotes are the single cell, like bacteria, okay? And eukaryotes, which were actually started to develop in the Eratosthenean era, we started to get eukaryotic life beginning to form. That's the the cells that have a nucleus and that actually eventually made us. Okay, so that kind of gives you a little bit of scale. So life first began in the Imbrium period, and then you started to get eukaryotic life in the Eratosthenean period. Okay. Okay, my slides won't advance. Oh boy, we're just. There it is. Okay. So the first period we're going to talk about is the pre-Nectarian. Okay, so you've got this, this impact happened, the moon begins to coalesce, okay, and it's really just an ocean of magma that's out there. So picture it that way. And the crust, as it starts to cool, a thin crust begins to form. That's your pre-Nectarian era. And this happened around 4.5 billion years ago. So quite a long time ago. And so the major, the major event that happens during the pre-Nectarian is the South Pole Aitken's impact. Okay? Now, this is something we weren't aware of until the late 50s and early 60s, when we started to put orbiters taking pictures around the moon, because this is on the South Pole and kind of leaking up onto the opposite side. So you don't really see it. But here's a photo. So it has the distinction of being the largest, deepest, and oldest impact basin on the moon. I mean, it's absolutely huge. It's 1,600 miles wide, 4 to 5 miles deep. I mean, that's huge, right? Huge impact. They estimate that it was a 140-mile diameter object that hit the moon. And you can see it here. It kind of traces out this way. See? Yeah, this crater Aitken actually defines, one of the borders, but it comes all the way down here. So it's huge. This is the South Pole, right? So it's kind of, you're kind of looking at, the South Pole tipped toward us and, up to the opposite side of the moon, right? So not the side we can see. But you can see it hit at a low angle because you can see the material piled up here, like it kind of came in from this direction. Didn't hit straight on, right? It kind of came in on an angle, wham, right? Made this huge impact basin. Now, unfortunately, we don't get to see this on our side, but when around the time of full moon, you can see some of these mountains that make up here. They're unofficially called the Leibniz Mountains, right? It's not an IUA approved name, but that's the name that it goes by. So you can actually see these, and these are very tall mountains. These are like half again the size of Mount Everest. So you're talking, 30 to 35,000 feet high, these mountains. You can see them from our side. If you get down the southern, around the time of a full moon, you can see these mountains. So this all happened, between 4.2, 4.3, billion years ago during that Nectarian period. And I have another photo. This one is topographical. So you can see the purples are the lowest, the reds are the high, you know, the highlands. And again, you can see just the overwhelming size of this thing. It was just huge. And again, we didn't really know that much about it, you know, until we started, sending the orbiters around and some of the Apollo missions as they were orbiting the moon, were able to get some pictures to really kind of see the extent of this. It was relatively unknown until then. So then we move to the Nectarian period, okay, 3.92 to 3.85. Well, that's not very long, but it's only decimals here, but that's 100 million years. Okay, so this is a 100 million year period that happens here in the Nectarian, and the theory is that it began with that impact of the Mare Nectaris, and the moon at the time is experiencing a period of heavy bombardment. Right, these big objects are coming through the solar system, and there are a few theories on that. Number one is that the accretion disk was still forming, so there's a lot of debris floating around and shooting around the solar system. But a newer theory is that the gas giants have actually migrated to the point where they are today. They were actually closer to the sun and have kind of moved out. And the thought is as they were moving out, they were creating a wake of material that actually bombarded the inner solar system. Because we see evidence of this, Mercury, on Venus, on Mars, so that the inner planets were kind of getting bombarded as the gas giants were moving out further into the solar system. So that's kind of the theory of how this happened. And this is where the majority of the impact basins were formed. Also, there's a layer of debris. They call it the regolith, and it's about 2 kilometers deep. That's when this is formed, because we've got things just constantly pounding the surface, and it's just pulverizing the surface of the the moon. The ones that are smaller are pulverizing. The larger ones have hit so deep, that they're causing volcanic activity. And just for reference. This is the Mare Nectaris. Okay. Now, at the time that they came up with these, that they came up with these periods, they thought that Nectaris was the first one. But there's been evidence recently that maybe it was Serenity that was the first one. So we don't have the luxury of having been able to go to every one of these basins, and take samples and try to determine their exact age. But pretty much everything here was formed around the same time during this Nectarian period. And at the very end of the Nectarian period, we had another huge impact, right? And that's the beginning of the Imbrium period. So this is a little bit longer period, and this is about 700 million years in length, right? And so this impactor hit at caused the Imbrium basin about 60 miles in diameter. So not as big as the one that caused the South Pole Aitken, but still sizable, 60, right? And it made a 1,000-mile wide crater. So, I mean, a basin. So it's a huge basin. And it's thought that this was so violent that it caused volcanic activity at other parts of the near side of the moon. This thing hit and caused cracks in the surface that you had more lava, bubbling up and coming out of the surface. And another thought is, especially when we look at the picture, when you get to the sea of the ocean of storms, right, Oceanus Procellarum, that that the lava flows kind of compounded. As more lava spewed out, it was heavy, the crust was thin, the crust collapsed in places, causing more volcanic activity, right? So you kind of had this piling on, right? As more lava flowed from these basins, it got heavy, pushed down, and more lava started to flow up. So this is the Mare Imbrium. This was the impact that hit here. Okay, and it's thought that most of the lavas that are here, this is the ocean of storms, right? The Oceanus Procellarum. That most of the lava flow here came from the Imbrium basin, and that's kind of what the current thinking is, because this thing was so big, and so violent. And one thing we have to keep in mind is that the lava isn't like the lava we see here on Earth. It's very thick red stuff that comes out, right, and builds mountains and, you know, builds islands out in the ocean. You know, based on the content analysis of the, you know, content of material here, it's thought that the consistency was more like motor oil, okay, the lava. So it flowed out. So that's why you don't have, you know, cones, right, in many places, right, you know, volcanic cones, volcanic mountains, because this stuff was very thin and more flowed than it did build up, right? So it's something to keep in mind, that it was very, you know, like I said, very much like the consistency of motor oil when it came out. So now you've got volcanic activity, you know, taking place, you know, over this 700 million years, kind of all over the near side, you know, of the moon, because of these, you know, these huge impacts that cause multiple cracks in a very thin crust, right? The crust is still very thin on the moon at this time. It hasn't, you know, completely cooled. Okay, so then we move into the Eratosthenean era. Okay, so this is, again, this goes about 2 billion years. Okay, and so by the end of the Imbrium period, the moon pretty much looks the same way it does today. Okay, at about 3 billion years, because no major impact basins at this point. There is still some volcanism, but nothing really major, right? You got kind of these smaller activities going on, but you're getting many impacts of these smaller and moderate size that are just, you know, that are just pulverizing the surface. And that's kind of what's happening, you know, during the Eratosthenean period. And then, so closely after that, you get to the Copernican period. Okay, and I'm going to get to the difference between these two, right? So that's about 1.2 million years ago to the present time. Okay, again, fewer moderate impact events, no further activity. So from about 1 billion years ago forward, no volcanic activity left on the moon, right? There's no more happening. And you get two, two popular or two notable, craters that occurred during that period is Copernicus at about 800 million years ago, and Tycho at about 100 million years ago. So even when you look at that, 1.2 billion, these two are very, very close to modern day, right? 800 million and 100 million years ago. So, so that the region where these two, and the reason that we see this, okay, we got Copernicus here and Eratosthenes here. This is a really clear picture, but they're both here, in this lava field, right? And that's kind of where they, where they decided to kind of draw this mark. And if we take a closer look, you can see it a little bit better, right? So the way they divide the Eratosthenean and the Copernican periods has to do with the age of the craters. So they think the Eratosthenean craters are like this, okay? They're more eroded. They don't have a ray system, okay? They may be overlapped by other impacts. And then for the Copernican, you've got these rayed craters, okay? And that's the kind of standard that they use. They said, okay, rayed craters, those are newer ones. Those are in the Copernican era. The ones without rays, we're going to say that those are the older ones. Okay? And that's kind of when they first put this division together. That's the way they looked at it. Okay, but today there's actually some other ideas around this, right? Because they've looked at the rays aren't strictly a factor of age. Okay, it actually is also a factor of what kind of content is being thrown out of these craters when they get hit. So the thought was that the ultraviolet light from the sun, right, is kind of erasing, if you will, the crater rays, right, over time, right, that they're bleaching them and you don't see them anymore. But now there's some thought that, no, maybe it's what it's hitting is more of a determination of what's making the rays. So we still have this division between the, for the most part, it holds true, the older craters and the younger craters, but there's some new research on that is finding some different, some different information. So what I'm going to try to do now, I'm going to try to play, I get this neat little video I found on NASA's website.
From year to year, the moon never seems to change. Craters and other formations appear to be permanent now, but the moon didn't always look like this. Thanks to NASA's Lunar Reconnaissance Orbiter, we now have a better look at some of the moon's history. The moon likely started its life as a giant ball of magma formed from the remains of an impact on Earth about 4.5 billion years ago. After the hot material collected into a sphere, the magma began to cool, eventually forming a crust on the surface of the moon with the magma just underneath. Around 4.3 billion years ago, a giant impact battered the moon's south pole, forming the South Pole Aitken Basin and sending debris as far as the opposite side of the moon. This impact marked the beginning of a period that would cause large-scale changes to the moon's surface. One by one, more huge collisions shaped the terrain, some forming large basins that would eventually fill in to become the dark-colored patches of the moon, known as maria. They began as normal craters, but soon started to change due to the size of the impact on the relatively thin crust. Because the moon had not yet fully cooled on the inside, lava began to seep out through the cracks caused by the impacts. The resulting volcanic activity spread lava throughout the craters, gradually filling them in and cooling. Because of the high iron content of the basalt in the rock, the maria reflect less light and therefore appear darker than the surrounding highlands of the moon. Around 1 billion years ago, volcanic activity ended on the near side of the moon as the last of the large impacts made their mark on the surface. The moon continued to be battered by other impactors, although they were much smaller than the objects that formed the largest basins. Some of the largest, most recent, and best-known impacts from this period include the Tycho, Copernicus, and Aristarchus craters, which are unique due to the complex system of rays that stretch out from the impact site. Finally, we arrive at the moon that we see today. Though the surface continues to be affected by impacts, the rate has slowed down drastically to the point where the moon appears unchanging to the human eye, as a permanent record of its own history, and a glimpse of how craters may have formed here on Earth.
So that was a little video. It was a little bit jerky on the, I don't know, through this, maybe it's through the internet or through the wireless, but it's so that kind of goes through what we talked about. So, in summary, the moon evolved, primarily through the action of impacts, impact cratering and volcanism. We've also, besides the moderate impact and limited volcanism, we know that, for the last about 3 billion years, the moon pretty much looks the same as it looks right now. And we always have to keep in mind that, our current theories about this, which is much of what I've been talking about is theory. We don't know for sure, but it's based on the limited samples that we've gotten from the Apollo mission, from the data we've collected from orbiters, and even from some Earth-based analytical methods that are used. So, this is an area that's always changing, and in the recent recent new interest in the moon is encouraging much more research. So we'll probably see more happening and more new things being discovered about our nearest neighbor, the moon. So with that, I will leave you with one final question, to ponder through your day here at Astro Assembly. Why do we call our moon the moon, but we give names to all the other planets' moons? Why don't we give our moon a name? Why don't we just call it the moon? Right? It's kind of like saying, you got a brother and you just call him brother. That's it. You don't give him a name. You just call him brother. But I also wanted to, again, just give a quick plug to our Skyscraper Lunar Observing Group. What we do as part of this is through the Astronomical League, of which skyscrapers belong and which any of you can become a member of for a very, very nominal fee. But they have a certificate and pin program. So where you find 100 objects on the moon, and they give you the list and the checklist, and you use binoculars you use naked eye and you use telescope. And when you get those 100 objects, you send in the information and you get a certificate and a pin through the Astronomical League. So we started our group, from the skyscraper. So we meet bi-weekly for a call that we, talk about our progress and talk about different things on the moon and even other astronomy topics sometimes. But so we started this in January, so it's been going not quite a year. I'm proud to say I actually did complete the 100 objects. I got there, right? It took me 7 months, right? I finished at the end of July, so it took me 7 months. And believe me, January, February, March were very difficult times to be outside looking at the moon, right? Besides the challenges of the weather. But if you're interested, send me an email or talk to me here if you want to join the group. It's very informal. When you start these programs from the Astronomical League, there's no time limit. I'm saying you have to get 100 things and you got to do it in this. You take your time and you do it however you want, right? You take it, you can take it as slowly or as quickly as as you would like. But I will tell you, the challenge with the moon is being able to see the certain objects at certain phases. So you have to like time it, say, oh, I gotta, all right, oh, the moon's at this phase. I can click off this one, and this one if I can get out there tonight, right? And then you go out there to be cloudy, and you'd have to wait till the next month, right? But you could see those objects again. So it was a bit of a challenge to do it, but it was fun, and I learned a lot, right? And so, like I said, I'll take some questions now, but just again, be aware, I'm a novice at this. Most of this stuff I learned when I was putting this presentation together, right? And because I love to learn new things, so it was fun getting books and reading and figuring all this stuff out. So. Any questions? Oh, lots of questions. You were first back here.
Which resource do you use to not get lost in the craters? Which crater you're looking at?
Well, I recommended just buying any kind of a moon map. I like bought the one I bought was like an Orion. It's a laminated kind of trifold. And it's like $10 to buy it, and it's nice because it gives you a corrected view of the moon, and a real view of the moon, and then a mirror image view of the moon on the other side. So you can actually see what you're looking at through the telescope, and if you turn it upside down, you actually get an inverted view as well. But yeah, so we just use the moon map, right? Use the moon map to find the craters, because the checklist you get is just a list which has the names, and it does give you some times when to look for them. It'll say, 10 days, 20 days. It'll give you the different days to look into, what days you can go out and see certain features.
So thanks, Michael. Very interesting presentation.
Thank you.
So I have an unfair question for you. I totally get it that you recently put this together, but a lot of the graphics were for craters on the side of the moon facing Earth.
Mm-hmm.
There's a huge impact on the far side. It looks like a bullseye.
Yep.
So here's my unfair question. If in the future, different surveyor, robotic, whatever, can sample soil and date some of the craters, is there any possibility of, say, predicting that this impact, if the moon was not here, would have hit the Earth and altered evolution on our planet?
Well, that's, yeah.
See if you can try to repeat the question. Good luck.
But no, you're right. And I didn't mention and that's the Mare Orientale that's on that far side that looks like a bullseye. And the thinking is that actually occurred around the same time as the Imbrium impact. I didn't include it here, but as to your question as whether it would have wiped out life on Earth, that's anybody's guess. I mean, it's likely that those same big rocks that were hitting were hitting the moon were also hitting the Earth, because the Earth was at a very proto-Earth stage. But because we have a very different world here, right? We've got plate tectonics, we've got wind, water, weather. You don't see the lasting impact of, for something 3 billion years ago, it's probably already folded under the crust and is being regenerated generated on Earth, because we have, we have the plate tectonics, right? If anybody's familiar with that, the rings of fire where we have the volcanoes, we've got these plates that are floating on top of the magma. The moon doesn't have that, right? And that's why that surface has been preserved, because it had a much smaller iron core. It's not as hot as the Earth. So it cooled, and it's pretty much stays the same, where the Earth is very active. But good question, something to ponder. That we could have had to start all over again, because at that time, right, as I said, we only had single cell life during that period of of bombardment, and so we would have had to reset the clock, and who knows if it would have happened again. There's a question over here as well. Was there? No. Yeah. Ron.
Michael, I just want to mention, so I think some of the debate that's still going on amongst the scientists is that the data hit into the Earth upon the moon, and I guess they're still debating as to whether or not that impact was a direct hit or a side swipe.
Yeah, I've read is that it was partially it was a side swipe, because that's what caused, you got this, it spun up the Earth, right, to get to the rotational period that we have today, because there's a lot of momentum in the Earth Moon system, both in the Earth's rotation and in the way the moon is revolving around the Earth. There's a lot of momentum. That energy had to come from somewhere, and I think that's what it was. That it was this kind of glancing blow that kind of like a top, right? You set it off and it starts going. But there's also been some alternate theories that it wasn't one giant impactor, but maybe 4 or 5 very, very large impactors that hit at the same time, and then caused this huge ring of debris that that eventually coalesces. So there's a lot of research. Nobody denies that it was an impact, but now they're starting to get into the split hairs as to how the impact happened. Was it straight on? Was it glancing?
Also, there might have been 2 moons that developed.
Right.
2 moons, 2 individual moons that are one, and then they came together.
They came together. Yep, I've read this. So there's a lot of theories about how the impact took place. Once the impact seems to be pretty a pretty solid theory today, and now they're kind of most of the new stuff is about how that happened. Jim,
have you tried sketching the moon?
I have not.
So that first slide that you started off with, that wasn't your sketch.
No, that first slide is actually that's from an antique drawing that somebody did, I think, back in like the 1700s. Something like that. Yeah, that they actually sketched it's an antique sketch of the moon. It's not my sketch. Mine would have had like a face and a stick figure. Right? That's about the extent of my drawing capabilities. Although I have been drawing double stars, because those are a lot easier. You just do dots. Right? Make one dot bigger than the other dot. Yeah, it's the bright one, and it's a dimmer one. One in the back.
Michael, great time.
Thank you.
My Atmos friends are going to roll their eyes now because you're going to let me talk about the moon for a second. Because I'm a big proponent of observing the moon.
Oh, great.
I don't so much have a question as much as a recommendation for folks in the audience. When I look at the moon, and I look at it a lot because I really love it. I know we can see all the big things, but I always take it on as a personal challenge to see the smallest craters I can see with my telescope. And if you've forgotten how much detail you can see on the moon, then you owe it to yourself to break out your telescope and point it at that thing and have at it. There are isolated craters that you can see with a medium aperture telescope that are on the order of a couple of miles across. And so I always find it a challenge to look for those really tiny craters when the lighting is correct, and especially if they're isolated. If you want a nice starter way to get introduced to that, find the isolated mountain Python, which is near Copernicus and Eratosthenes. Yep. And just to the south of Python, there are 2 craterlets. They're very simple craters. One's about 4 miles across, one's about 3 miles across. And it will amaze you that you can actually pick those out with anything bigger than probably a 4-inch telescope. And so just something to think about to make your lunar observing a bit more interesting. The lighting changes every month due to the subtleties of the moon's orbit. And so there's always something new to look at. I always see new things. So how did I ever miss that?
Yeah.
And so just have fun with it. It's a great object. And if it's too bright if it makes it too bright to do deep sky stuff, we'll do the moon then.
Yeah, absolutely. That's how I get into it. Great. Thank you.
Yeah,
thank you for that. Any other questions?
Yeah, that was very interesting. I think it might even be more interesting if you continue your evolution of the moon and the earth and life on Earth, because the theory is that without the moon, life probably would not have been able to develop on Earth. I just wondered if you might want to look into that. a little
Yeah,
bit more.
that's, I mean, certainly, right? I mean, that's the reason, we have the tides, right?
Yeah.
Tides are a big part of, a big part of life, right? And that, yeah, that's great. I've been actually looking at I did read a lot that I didn't include here, but I've been reading a lot about the geology, of the moon, the different, the different materials and where you find them and where, so like I said, you can always go like that next step deeper, when you do these, right? So great point.
One suggestion I would offer, I can't remember the author, but there is a book that what if we had no moon? It's a very interesting scenario, what happens, and it was really details, really good.
Wow. Yeah, I'd like to read that. That's kind of neat.
But I got a counter question relative to that. We also have we have tidal effects due to the sun. So we may not have had the depth of tides that we experience, but we still would have seen tidal effects on the oceans. Just not as, we probably would not have evolved to land walking animals as early as we did.
So is that a recently published book or?
Oh, it's got to be maybe 20 years.
Okay, it's so relatively recent.
The author wrote another book, what if we had no moon?
Then read Flatland.
Yeah, that's right. I've read that. I read Flatland.
When I've read the moon, and I'm no expert on this, but from what I read, the moon also stabilizes the obliquity of the earth, the tilt,
Mhm.
which long term, which makes things better for us.
Right. So in other words, it would wobble more if the moon wasn't there to kind of stabilize it. Yeah, I could really mess with the seasons, huh? Because right.
Yeah, I did some research of my own for that, and then same thing, yeah, it would be, they're talking about climate change now,
Yeah, this would be.
and especially after Ian hit, everything's been, they're already connecting it to, right?
Of course.
So yeah, it would have been like, forget it, the earth would have been,
Wobbling all over.
Wildly mutating polar scenario. I think the moon does have a name. Luna.
Okay.
Maybe that's my own lunatic way of thinking. But
There's another Selene.
That's right. Selenology, right? Is the study of the moon.
those are just different languages that mean moons. Right.
Yeah.
That's a point.
we got a Native American here.
Right.
Years ago,
Right.
and Native Americans, remember, they tried to just refer to the moon as mother.
Right.
Anyone else?
Just one more thought. You mentioned the Leibniz Mountains on the southeastern quadrant. Basically far side objects, right?
Right.
As is the basin rings of the Oriental Basin.
Mhm.
So another thing that mind blows is the libration of the moon, where you can see that, over the course of time, 59% of the moon. And there are lots of ways to figure out where the moon is in its libration right now. But I always like to look at the Rook Mountains and the Cordillera Mountains around the Imbrium base, the Oriental Basin.
Mm.
And you're right, the Leibniz Mountains are actually pretty stark along the terminator, along the limb, when they are tilted just the right.
In the right way,
Right,
right?
yeah.
Right.
Yeah. And then going with your AL 100, you must have seen the marginous swirls.
Mhm.
That's another thing that really counts on vibration too.
Right.
Just
Right.
want to bring that part of the moon, that eastern section of the lunar east into view better. Yeah, you also from the new lunar observing.
Okay.
Thank you very much.